Okay, so brief introduction then. My name is Randy Schuster. I'm a mechanical engineer. I'm going to be talking to you about medical research. Kind of an odd thing, but it works out. We just found, this is Nick, this is Bryce. They're members of the team. We have a pretty large team. Professor Samudio, Professor Ayung, myself, Professor Storr are the four sort of content managers that can help everything run. We're working with Berkeley National Labs and Mount Hood College as the whole thing that brings us together. But overall, we have a group called StudentsGiveHope.org. This is a group that was started by Professor Ben Samudio. He is a CAD, believe it or not, he has his PhD in CAD, which I thought was computer-aided design and drafting, but it's not. It's computer-aided drug design. That's what he got his PhD in, and he came to us in the Design Hub about 2.5 years ago and started this long, lengthy process that we are just getting our hands on now. So we have this cool thing. I'm going to tell you a little bit about StudentsGiveHope.org, but it has developed into OpenDD Project, which is Open Neural Network for Drug Discovery. And we're going to talk about that for just a little bit here. So what are we going to go over? I'm going to talk a little bit about StudentsGiveHope.org, what the OpenDD project is, the Design Hub, and then our interns are going to take over, and they actually know what's going on. They're on the Skype meeting every week. They're doing all the work. I basically get money and resources for them. And I sort of talk their language a little bit. So, so let's get into a little bit about StudentsGiveHope.org. This is an organization that is dedicated to open source research. The way most drug research happens is some drug company identifies a market. So that means that either they can charge a lot of money because everybody's getting sick, or they can charge a lot of money because it's such a deadly problem for one person. And that's where they put their effort. It does take millions and millions of dollars to develop a drug. So you can see why they do marketing first. Well, there are a few people. Professor Samudio is one. The rest of our team are others, and we're not the only ones, that believe that open source research, crowdsourcing, can be just as effective because the biggest cost is in the initial research. What might work? And then the drug companies can get on it and really get focused. So if we could, in some fashion, do open source research, then we'd be helping out, crowdsourcing. And so StudentsGiveHope.org is dedicated to that. And we started about 3 years ago just making little cardboard, we tried to make 3D printed models. That's why he came to me, but his scale was too big. I thought he wanted some little thing. But our scale at 1 angstrom equals 1 inch, an active site, part of a protein is like this big, and our 3D printers are this big. So then we got this great idea, we'll take it to the plasma cutter, because it's 4 feet by 8 feet. And we made this very cool plasma cut thing, took it to the state fair, had tons of people interested in it, and found out that nobody else could make it, because most high schools don't have plasma cutters. So that didn't work out so well. So then we got into laser cutting cardboard and wood. And that was a winner. We got it out to about 5 high schools, got 900 drug designs done, and amazingly, 3 of them qualified to go on to Novartis into their pipeline. So 3 out of 900 is actually considered a good number. One of those was done by a 9th grader. So that's what gives us, when we say students give hope, that's what gives us this idea that if we could crowdsource it, it would be cool. So the next thing we did is we started trying to see how fast we could generate Luke GH and Zika and other versions of SARS, and we found out that it was kind of cumbersome. Wouldn't it be nice if instead of looking at things like this is an output from a student for a little bit of medicine, wouldn't it just be great if they could visualize it in real time, sort of like Magic School Bus, be in there and point, and the stuff would all come up, and we could get the feedback right away. And so we made a little model. I'm going to show you that in a little bit. And the kids just glommed onto it. And it didn't even do anything. It was more like Pong. It went back and forth. Nothing really happened. But we saw the potential. Unfortunately, in game time mode, it takes us maybe 5 to 10 minutes to complete the cycle. They put something in, it goes to another compiler. The compiler sends it to the web sends it to an analysis thing. It comes back, we put it into a compiler, it comes back, and 5 minutes have gone, and they're playing Minecraft. So it's not gonna work for us. That's where these guys come in. They're gonna develop our speed burning process of doing this and our gamification. So that's the idea behind StudentsGiveHope.org. How can we have an open source platform that can get these things uploaded and generated quickly and in a way that we can actually get thousands of these done into what Bryce is working on, which is a deep neural network. Okay, so Nick's job is to make it fast, and Bryce's job is to get data back and forth. And then we have other jobs in the whole thing. And so that's StudentsGiveHope.org. It's open source, and we're just hoping that everybody will want to jump on board and do some cool work with it. We do have the physical models. If you're interested in your classes or over the summer on working with us, we can hand you the physical models and you can start doing this on your own. So it's kind of cool stuff. Man, there's all sorts of stuff on here. Look at this. This is just wild stuff. So these are some of the ones. And so what comes back, by the way, when you dump this into the program, the analysis program, it gives you a grade. This is a pretty good, A grade. And so that's one of the ones that would go on to get further checks. Okay, and so you can see these were all done by, most of these were done by junior high and high school students. So not too bad. Now we're starting to get Professor Samudio says that these are still better than what he was getting and faster than when he programmed his process. So that's why we have hope in this. This QR code, by the way, right now goes to a virtual reality model. So if you get to this and you got virtual reality glasses, you can kind of look at your cool model and see what's going on. So we're getting there. We're getting close to being really high tech. So that's StudentsGiveHope.org. The OpenDD project, I want to talk about a little bit, has gamification. That's our primary goal. We figure that it's great to get this out to high school teachers and college teachers. Guess what? They are busy up to here. It's hard to get them in on the project. If we can make a game out of it, where that game is giving us good data and it's fun to play, then we got a good thing going. We'll get data like crazy. And it's research at the primary level. So when you look at something like this, it takes a real drug designer to figure out what that means. But if you're just playing a game where you got to match yellow to yellow, red to red, blue to blue, and then it gives you a score real quick so you can start adding more or changing, we think we got a pretty good gamification of it. So we're really talking about the primary level. After this level, there are a number of things that still have to be done. If you grade out, what are they grading this on? Total energy, bond energy?
Single point energy.
Single point energy. I don't know what that means. It means something to, do you know what it means?
I do not know what
Bryce knows what it means? Okay. I have no clue.
So the single point energy is like the interaction energy of the drug molecule with the activation site of the protein molecule. So like if a drug molecule is a really good fit inside of, like, let me back up one step. So a active site can be blocked by something called an inhibitor. And basically, we're trying to find the best inhibitors for activation sites. And the way you do that is you find like a drug molecule that has a very low interaction energy with the active site, because the lower the interaction energy with the activation site, the snugger the fit is inside of the inhibitor, or the space where the inhibitor would go. And so yeah, we're basically trying to find the smallest interaction energy.
Cool. So what happens after we get that interaction energy, there's a whole bunch of steps that go on. There's 7 categories that Professor Samudio's program goes through to see if it's actually a useful thing to pass on to the drug. So there are things like, will it attach to a drug carrier that will go through your body? Is it something that your body will attack? Is it a molecule that is stable enough to last a day or 2 or 3 in the body? So there's all sorts of these, and then they also have a wide range of these that have already been proven to work somewhere else. So that's another one. So those are some of the ones that I know. So we're the first step. That's what we mean, research at the primary level. Any one active site will have maybe 1 million or 2 million possible molecules that the drug companies would be interested in looking at. So that's why we have the 7 other categories, and why it's not just a matter of, oh, I think I can just do one and that'll be good enough. Millions of molecules literally could plug that site. And so that's why it takes this big, deep neural network and lots of things. So what we want to do is gamify it somehow. So this was our first demo. We said this is a visualization of an active site. That one's actually SARS. Blue means one kind of molecule, black is another. And you can see how complex it is to try to get something to fit in there. So the idea of the game is that you can go through there and you can attach molecules where you want it to go. So that's the most simple version of a game that we thought of. And where are we? I keep getting out of this. I should do another tab instead of doing the same one. So we want to gamify it. Now that wasn't a very fun looking game, but when we stuck that at the table at the Maker Faire, it was mobbed, and not just by kids. We had tons and tons of kids. So we wanted it available to all sorts of people. So this was sort of our first round where we were plasma cutting. But even with the plasma cut model, you could see we had people all over it go, what is that? I want to try that. I want to do it. So you see how up here, this one model kind of looks like that cutaway that we had, right? And these are the little models that go into it. And literally, you physically put these together and try to make it. Kind of cumbersome, kind of hard to do, but it could be done. So that was our first go through at it. And then we wanted to do a little bit more advanced. So we took different types of models to the Maker Faire. You can see it looks, this one This one is Luke, that doesn't look like SARS to me. Maybe it's Luke GH or something like that. It's a little bit different one. But you can see it's not quite as clunky looking, a little bit easier. We've got the gamification of it. And it was just a mob scene. We probably had 100 people. And here, this kid's looking at it in VR. So that's our next goal. If we can gamify it, we can actually get you inside the molecule and just looking around. So you'll be graduated. Sorry, you don't get to play. He'll get to play. So if you have any skills in VR, we want you, or skills in chemistry or whatever. So we want everybody. And we had physicists, we had chemists, we had high school teachers, we had professors. This is how we got hooked up with Mount Hood, is they met us at this one and said they wanted to collaborate with us. Cool?
I actually had just a small comment on the open neural network part of it. And so the whole reason that he's saying like we want people to play it is because the neural network is just statistical analysis. And the more that it gets played and used in all this stuff, the better training it has and the better data we get. The more data we have as well.
Yep, and so that's where we come in to talk about training the neural network, which that's way beyond. Do either of you know the neural networks? You do. Okay, maybe you can talk about what it takes to train a neural network, because it's just a bunch of computers all hooked together, right?
So right now, as Randy was saying, we were working with Professor Samudio, and Professor Samudio is going to be getting us a set of probably thousands of associated images with like associated single point values or interaction energy values with that. And so what we're going to be doing with the AI is we're going to be feeding those images in with the single point interaction energies to train the artificial neural network. And then we're going to be using the neural network to cut down on computation time, because as said before, it takes a few minutes for each calculation. But if instead of like sending each individual molecule through all of those calculations, we can just compare it to to images that have been seen before with associated interaction energies, then we can cut down on computation time by a lot.
Cool. The whole neural network thing is sort of, I mean, I was a Fortran guy, 1 by 1 by 1 by 1 by 1. And the whole neural network thing is it's supposed to act like your brain, right? So there's tons of stuff going on in there, and when you see something, you recognize it without having to go through every single permutation. So I don't know how they actually work, I just know they work. And we're working with that. So that should lead open source neural networks leading to our first level drug discovery. So that's what open neural network for drug discovery is. And we're not the only people working on it. We're the only community college working on it for sure. And at this point, we're the only people that are working. Well, there are open neural networks. A lot of people are dumping this into this, but we seem to be the only people that we know of that are gamifying it to really get it open. What most people say is open is they share their files with other chemists that know about chemistry. At this point, we don't know of anybody who's trying to get this to the point where just the action of doing the game gives us information from the neural network. So we're cutting edge with American River College, yes indeed. All right, so that's the open project. I want to talk a little bit about how the Design Hub fits into this, and we really call it the Design Hub because we're sort of the spot in the center, right? There's a kind of a famous saying from Lao Tzu that says the useful part of the wheel is the hub. there's nothing there, but that's what everything goes around, and it supports everything else. So the design hub isn't really a thing or a place or anything like that. It's just a group of people that all get together to start working on stuff, and it's a place for us to gather. So we've got on this project, we have art new media, we have programmers. We actually have programmers from kind of two different sides. We have the programmers that know computer programming for game design. We have programmers that know just how to work with data. And we have programmers that are getting into this AI weird stuff that I don't know if they even understand, but they know how to do it. And so we got a big group, and we've even had welders, we've had laser cutter people, we've got web designers that are ready to work on this. So even if you don't think that you're a chemist, we have interest in this. And soon, after the summer is up, we need game players. We just need people to play the game and start getting input. So, and you don't have to be a ninth grader to do that. You could be a college student or a professor or a staff. It doesn't really matter. You can have your kids do it. That's what we need. We need to get to the childhood center, early childhood care center. Get all those little 3-year-olds on it, right? They'd probably do better than we do. So we've got a lot of stuff going on. We've got chemists, programmers, game designers, computer science techs. So there's the other thing that we're just starting to work in, and I think you're working on our backbone, right now? You know, what's it going to take to get our computations running?
Yeah. Actually, go back one slide for me, please. So this right here, image A. So I take a file. Basically, so in real life, humans, we can't look into a microscope and see every part of an atom. They're too small. So they put them in these controlled environments, these molecules, and they shoot photons at them, and they get certain hits. And where it's going to hit is going to be the nuclei of certain atoms. And so we're going to have a file that just has a list of atoms and where they are. And then, so that's going to be the main, the main centers, I guess, in a sense. And then there's going to be electrons and stuff around them, but we're going to encapsulate them in this. You can't actually see the grid, but we're encapsulating it in a grid such that we can target certain parts of the molecule. And just like how you saw in the video of the molecule connecting in certain places, the reason we do it like this is such that if I put it in here, all these other boxes of data are not messed with. And so that's what I'm doing. Yeah.
Right. And then you're going to start talking about what it takes to get up to the cloud and back.
Yeah, I also am setting up the interactions between the neural network and the game itself. So it would start with the mol file, and that would be your active site. And then we'd have a bunch of different drugs that could be potentially used and tried out to work with it. And so you would put your drug in some place on the active site, and then that would get sent to our remote server that has the neural network. So it's going to go into the neural network. We're going to get the grade that comes out of it, and then it's going to come back and tell you basically what you need to, if you made a good decision or not. Yeah.
So pretty crazy. So I'm gonna tell you how it works in my very simple mechanical way. So if each one of these little dots here is a blob here, it's really a whole bunch of photons, a whole bunch of neutrons, and a ton of electrons. And so every molecule, if we wanted to make it a point cloud, might have 100 parts to it. And this thing has thousands of atoms in it. So that would be thousands of atoms times hundreds. I'd have hundreds of thousands of things to keep track of. We're going to simplify it and just say, in this box right there, they call it a voxel, sort of like a voxel, but it's a voxel. We're just going to say there's 3 neutrons, there's 4 protons, and there's 150 electrons. We don't care where they are in there. And that's why we have to train the deep neural network to go, oh, I get it. That's pretty much like this other thing that was all spread out. We can kind of make a comparison. So we have very, very few pieces of information. Instead of having maybe 200 pieces of information in that box, we have 3 numbers. And those 3 numbers pass into a grid. The grid passes somehow to some cool thing that Bryce is going to work on, don't know that, and pass back. So it's a simplification. It's just a way of simplifying it and coding it, which is like, wow. So that's where we go from point cloud configuration files. That's what Sean is working on with Professor. Is that what Sean's job?
We've pretty much completed the point cloud configuration files. Like, that was a collaboration between me, Nick, and Sean.
Okay.
About 3 people worked on that.
We just arbitrarily used spheres.
Right. Okay. So now we're into what we call the data transformation and manipulation. Right. You're going from some file type to another file type to another file type to another file type.
Yeah, I can explain that.
Okay.
So, as I said earlier, it starts off as just a mole file. And so a mole file is just a file that has some atoms, where they are in space, and a little bit extra data that we're not too worried about at this stage. So we're going to take that, and I've represented it with that 3-dimensional grid, which, as Randy said, will have 3 numbers: protons, neutrons, electrons. So once we have everything in its place in space, we output that to a JSON file, which is basically just a way of structuring data. It's very, very commonly used in data transfer in web a lot. So from there, each block basically is going to be a voxel, you know? So it's going to say, here's the voxel, here's how many protons, neutrons, electrons it has, and here's the size of it in angstroms. And then, so from that, we're going to convert it into 2 dimensions. That part we're still working on a little bit more. So I don't know what file type that'll be. So, but once we send it to the neural network with the single point energy, the only thing we're going to get back from that would be a number. And that's kind of how the data gets broken down and transformed into different things throughout.
Cool. So that's where we're at with that. And then we've got our game design. Oh, any of you guys mathematicians? Anybody math people in here? So we understand that there's something or process called the Hilbert curve, which, and I use that in 3D printing, but I don't understand it either. So you can use these Hilbert curves are what takes the 3D map into a flat map in the most efficient way possible. So some mathematician named Hilbert came up with those things. We're looking for somebody who understands those to be on our team. So if you know any math people, send them our way too. I say I'm always recruiting, even in the middle of a presentation. Recruit, recruit, recruit. So our next thing then is a visualization and data packaging. That's through a program called Unity. That's a game engine. It's actually not a game engine. It's a visualization engine that interfaces with numbers. So that's what that'll be. And then we've got this cloud data management thing that we have to track down. Many of you, I am sure, have noticed that we don't always have the strongest cloud interface here at ARC. And this has to be a massively strong cloud interface for us. So we're working with our IT department to figure out how to get that done, what servers to use, how to get into the cloud, because we still have to protect data, right? We can't just like fling it out there. So this is not even it's the last thing we're attacking, but it's not the least complex or smallest portion of what we have to do. And that's really a different type of programming and computer science and the data transformation and manipulation. So those are the things we've got going on. Just as a quick shot, this was one early aspect of what we had going on, of what we had to do to get these transforms done. Now we're way past these, but it's still the same basic operation. It's just instead of going onto pieces of cardboard, we're going into a voxel space. So we would start with drag and drop data that was a CSV file, comma separated values, just number, 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 and each number had a color that represented what type of molecule it was. And we wrote a program that would call a Lisp routine that would place all those points. So when we talk about point clouds, this is what it would look like if we took a slice. So instead of voxels, cubes in space, we were doing it based on slices of bread. And this is where the salt and pepper would end up if you shook it on. All right? So we would have those, and we separated each molecule into about 50 slices, each 1 angstrom apart. And as we put more and more pieces of each color on, we would get a full slice, and then we had to put markers on it so we knew where it was in space. So this was the same process that these guys are going through, but we did this manually. So this would take us a week or a week and a half, and we need that to be a microsecond or a millisecond. So that's why we got the cool programmers involved. Once we got those done, we could start stacking them together. We would visualize what the surface looked like to know what it would look like. So that's where the neural network idea came from, was we would just look at these things and visualize. We trained a student with some artistic talent to read these things, trained them just like we're going to train the neural network to read these things and draw the shape. And once we got that, then it was easy for us to put it into the laser cutter, to make the different sets, put it onto the laser, and start cutting. Okay, so that's essentially the process that we go through, and we're not doing anything different, we're just doing it better. So that's what our system is for how we've done the active site process. And if you want to see just really quick, that's one set of subfiles that we had to go through before. So we had everything, for instance, in a SARS or a DNA or a LukeGH. We had each of these was just chock full of about 150 or 200 files. That's what it took us. So we know that we have to really, really simplify that, hence the gamification. We just want to game, talk, spit out a number. Make some sense to what we've got going there? Okay, so at this point, that's sort of what we do and what our project is and what our program is. I'm back in recruiter mode. We want students working on these projects. And so I'd like our interns now to tell us just a little bit, not about the project itself, but about their experience and what they've ended up doing through the project, and maybe follow this or maybe not, I don't really care. But just tell us about what is the internship like, what it's done for you, what you've gotten out of it.
So I'll try to stick in that order a little bit. So the final deliverable obviously is going to be a utility or game such that people can, crowdsource data for medical research, as well as gain some type of intuitive approach to these kind of issues. Some of the challenges that I personally faced in my aspect of it with the visualization is I had no idea what a voxel was. So everybody's heard of a pixel, right, on your TV. So a pixel is just some square that has, a color, a hue, a brightness, intensity, and all these things. And so how do you represent shapes with squares, right? How do you represent a circle with squares? Well, you don't do it with 4 squares. You take many, 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 many squares and put them in a circle, and you step back just the right amount such that to you it looks like a circle. And so that's also another aspect that I had to think about too with the game. So they're telling me to bring in these molecules and bring in the electron clouds. And as I said earlier, we were doing the electron clouds as just spheres. So anybody who's taken just a basic chemistry class knows that there's electron clouds, and they actually have functions that represent them in such a way. So not trying to steer back into the project too much, but another cool part of that is that we're kind of tricking the network to think it's actually the atom, because we're not really representing it perfectly. So that was, the biggest challenge for me was understanding that, taking that abstract idea and then turning it into something that you can actually just see happening. So that was that. Resources-wise, luckily, Professor Tack was there for me to ask a lot of questions. So he was able to help me clarify more so what a voxel was. I did do research on Wikipedia, and that's where I got the formal definition of, hey, this is a volume element. We just represent 3-dimensional space with this. But it does really help to be able to talk with somebody who does have a deeper understanding. Another one of the resources, especially because I was the programmer for this, the biggest resource for me was C++.com, as well as the classes that I have taken here have given me some kind of a knowledge of structure, to how a program should work, run, and run efficiently. So collaboration with my colleagues. So I had to do the visualization, but that mole file that I was talking about, I didn't write the code to extract the atoms out of that. So what my specific program needed was just the atoms in their XYZ place. Where are you? So we had another intern, Sean, who wrote something to extract the data I needed out of that mole parse file, and that's how I used that. And then Bryce did the electron cloud representations based on the radii of the atom, corresponding atom. Preparation to do this work, a lot of reading. And then, so actually, one of the first preparatory tasks that Randy gave me was, can I create a smiley face out of cubes? And that was kind of what I was talking about to you with the circle, right? Can I take this image and refine it, make it less resolved, make it more resolved, and then also target specific points of it and change them a little bit? So that was a little bit that we do. Furthering my education on this, I would say right now, so the next step for me is building the environment, right? I have never dealt with a server before or anything like that, so in terms of furthering my education, the next step for me is going to be understanding setting up computational environments and how to set up how a job is defined, how a job queue works, when we stack up multiple jobs, or how batches of jobs might be handled with right privileges and stuff like that. Yeah. And so that was just a little bit about my part.
All right, and yeah, I've had a really good time on this internship so far as well. It's really fun. You get to collaborate not only with students, but also with various other professors. As Nick said, Professor Tack has been a huge help throughout this whole project. He's very smart with pretty much every computer science, logic-based
And if he
problem you
doesn't
might
know
have.
it, he learns it overnight.
Yeah, he's
It's like
very
really cool.
dedicated. And Samudio has also been a huge help. But students like Nick and Sean, and even people who aren't involved in the project, have also been a huge help. There's pretty much always people on campus who know more than you, so it's been a very good experience collaborating with, even people that are just like in my math classes or CS classes that aren't involved in the project. So in terms of challenges, coming into it, this is my first experience with artificial intelligence, but yeah, I've read up countless hours on it, and I finally have a pretty good understanding of it. Let's see. Other challenges is, yeah, we had to come up with a plan on like how are we going to feed the artificial neural network, and like are we going to be feeding it 3D images, or are we going to be feeding it 2D images? And so there were many things that we had kind of had to like consider in terms of computational time and what resources we have. And I think, yeah, this is going to be great for my overall education, because not only am I learning a lot about neural networks, which is a super hot topic right now in today's society, but also we're planning on publishing a paper by the end of this, and so it'll be really awesome to have all of our names on a paper that's like publicly published. Yeah.
Cool. So, that's our presentation. Do you guys have any questions for us or for the interns, or?
I'm going to ask if folks have questions, could whoever's going to answer the question repeat the question before you answer
Oh.
it, then we can pick it up on video. And folks who see this later are going to be able to follow along.
Cool.
Thanks.
There we go. Do you guys have any questions or comments or?
All right, well,
Yeah.
I'll start. What the heck? This is great. I thought it was awesome. I'll make a question here. Which do you think is like the coolest part from your perspective? I mean, like here I am. I'm a non-scientist, and I'm thinking, wow, is it the game design? Is it understanding the neural networks and the artificial intelligence? Is it constructing the models and then sort of taking those and turning them into something that can be accessed online?
So
Okay.
Let's see. Well, I'm going to try to repeat that question so that we can. What's the coolest part? There. How's that? Cool.
Well, yeah, so basically, in the beginning of the project, we were all asked what part of the project is most interesting to us, and they basically assigned us to whichever section of the project that we showed the most interest in. So it kind of shows by who's in what category of the project. But yeah, artificial intelligence was super interesting to me. So that's why I chose to be in that part. I know it's just super up and coming, and there's so much you can do with it. So I thought it would be an amazing place to start.
For me, I chose to do the visualization because really what I enjoy is watching an abstract idea or process become reality. And that's kind of the idea of like what's known as like an algorithm, right? You have this idea of I can take this and I can make this happen, but how do I do that? And I like just seeing things just happen, really. So that was why I chose the visualization part.
And I'm going to jump in. So when Professor Samudio first brought this to me, I saw immediately that we needed more than just a 3D printer, more than this, more than another thing. And the whole purpose of the Design Hub is to be multidisciplinary and bring that all together. And I'll tell you, there is not another college around here that can do what we're doing in the way we're doing it. They're trying to do what we're doing at UC Davis. They have a design group, and they're coming to us for help. So that's very, so I think it's really cool that we have such a good multidisciplinary project group that we can draw on, and that everybody's willing to work together. And it's a powerful thing. So for me, that's the cool part, that we get to do all this. Yeah.
So for this whole idea of gamification, does it have like a, I don't know how to say this, but like a basis model where later on you can like apply it to many things in biology? Like I know some of my friends and I really struggle with like understanding what like different microscopes, because we need to understand how they work on the inside, like electron microscope and things like that. And there are no videos on YouTube that can explain it. So we were all thinking that if we could play something on our phone that would
Cool. So the question is once we've got this done, can this be applied to other areas where we can generalize what we're doing here to be used in lots of other aspects? What do you think on that?
So I will say that our group specifically doesn't have those plans at the moment. But as Randy said, this is a whole open source project. Everything that any of us have ever done, you can go right online and download it. My code is online, his code is online, everything is online. It's open for the public. Anybody who wants to take what we have and add on to it can. And that's the whole idea of open source. So if you had that idea, maybe you might not be a programmer or something, but we also do work order requests here, so you could bring it back to the Design Hub, of course, and we could make it happen. But, you know, if not, it can be developed by a community of people, for sure.
Do you have anything to add to that?
Yeah, so I know at the moment we're only working with SARS, and we're planning to incorporate like many other viruses, but I do not think at the time we have plans to expand it past that. But I think maybe once we finish like with the viruses and stuff, we could possibly expand our horizon.
Are you looking into like CRISPR, the virus, you know, redoing the genome? Have you seen that as like an injection, virus?
Well, actually, we're working with Sac State to do some DNA modeling in this very same way. I think once we have this process of voxelizing, which is becoming bigger, you're gonna soon see voxelizing TVs. So so we're sort of like at not the forefront, but we're catching the wave. I think we're gonna see a lot of this, but I'm gonna tag on to this question here a little bit too, that they don't know about because they haven't heard about it yet, or maybe you have, but we are also in a process with Professor Xuen Young of creating an AR/VR, augmented virtual reality presentation of physics of high energy particles. Now that's actually just his starting point to see if we can do it. His goal is a UC Davis project actually, which is to try to figure out visually the physics behind the Twitterverse. So if you get that, so there's literally billions of points of data out there, and there has been some work that visualizes that, and it looks like the universe. Clumps of data come together, and they seem to attract other clumps of data, depending on what the period is, the topic is, who's giving it. So there seems to be, I'll put it as attractive and repulsive forces in the Twitterverse. And he's very interested as an astrophysicist of comparing astrophysics to Twitter physics. And so, yes, we have plans on doing other cool stuff with this technology. And yes, we can do other cool stuff once we have the technology down. I think it's going to be, I think it's going to be huge just what's going to happen around here for us. Cool. Any other questions? Who wants to join the hub? Raise your hand. There we go. Okay. So the last thing is this goes up on how do they get to this stuff if they want to see it again to get resources?
Well, I mean, I'll videotape it, add the slides, and we'll go on YouTube. But with some of his websites, I try to take video videos. And then if there was other resources, if I don't have them, I can't.
Does College Hour have a place where we can post the presentation?
Send it to Christina and we'll figure it out.
Okay. If you don't, the Design Hub would be glad to help you along with it. There we go. Okay. All right, well, thank you guys very much. Here's a round of applause. Here we go. Thank you guys very much, and now it's back to programming. There we go.